Okay guys, so now we are on heating test on salts, right? Second video. So in this section basically we are going to heat up salts and they're going to release certain products, and based on the products released we are going to identify what the salt generally is. Okay, so not a big deal. Let's just go through here. So let's say we have salt A. After heating it up, right, it produces, so we put the arrow for to heat up, right, it produces product A plus product B plus product C. Okay, right, so in this scenario, let's say product A is a metal oxide and product B is, let's say, oxygen, product C nitrogen dioxide. Okay, so from here we can see, okay, so it forms a metal oxide, oxygen, nitrogen dioxide. This the only the only type of salt that releases oxygen and nitrogen dioxide are nitrate salts, you see. So from that we're going to go like, oh, okay, that means salt A, the anion is nitrate. It's a nitrate salt. The cation, we need to do further tests to know exactly what the cation is. Okay, but we have already identified, okay, in this case the anion is a nitrate, so it's something nitrate. It could be potassium nitrate, sodium nitrate. I'm just giving examples, right? Okay, so on and so forth. Okay, so basically that's what we're going to do. Okay, so we are going to see what are the different products that are released, and from that we're going to deduce what type of salt we actually are dealing with. Okay, all right, let's continue. Right, so I'm going to read through this with you all. So number one, all ammonium carbonate, nitrate and some sulfate salts will decompose when they are heated. All ammonium salts. So now we're starting with the first one, ammonium salts. That means any of these salts, whether it's ammonium carbonate, nitrate, when you just heat them up, you don't have to mix them with any other substance. You just heat them up on their own, right? They will break down immediately, and that is called decomposition. So they will decompose immediately when heated. Look at number two. We're starting off with ammonium salts. So ammonium salts will give off ammonia gas. Okay, liberate means it produces or gives off, right, ammonia gas when it's heated up. So in this case, it's very simple. Any ammonium salt, it applies to any ammonium salt. Here they've just given some of it. So ammonium nitrate will give off, if you heat it up, it'll give off ammonia gas and hydrogen nitrate gas. Okay, you cannot call it nitric acid. It is only nitric acid. It's only nitric acid if this is aqueous, right? If it's not aqueous, you can't call it nitric acid. It is hydrogen nitrate. Okay, so please bear that in mind, right? So again, that's that. Second one, ammonium carbonate, right? You heat it up and it'll decompose and produce ammonia gas, water and carbon dioxide gas, right? That's ammonium carbonate. Third one, ammonium sulfate will produce ammonia gas and what? Hydrogen sulfate, right? Okay, hydrogen sulfate. It's liquid. It's not aqueous. If it's aqueous, then yes, it becomes an acid, right? It'll show it acidic properties. So now we just call it hydrogen sulfate. Okay, the point is, it didn't matter. All three of it were ammonium salts. We were heating up ammonium salts, and all of it released what? Ammonia gas. In other words, if ever you heat up any salt and the gas it releases is ammonia gas, one of its products, just one of its products needs to be ammonia gas, and you already know you're dealing with an ammonium salt. So you know the cation in that particular salt is ammonium, NH4 positive. All right, so okay, it's a bit big, let me. Okay, so let's just bear that in mind, right? That's basically, ammonium is very simple. They've given you 3 examples and you already have it all. Let's go to number 3. Number 3, we're moving on to the next group of salts, for carbonate salts, right? So all carbonates other than potassium carbonate and sodium carbonate will produce carbon dioxide gas when you heat it up and decompose it. And table 8.12 will show the effects further. Anyhow, guys, so basically they're telling you, if you have a carbonate salt and if you heat it up, right, it will decompose and break down on its own, and one of the products it produces will be carbon dioxide gas. This applies for all carbonate salts except 2 carbonates, the two most reactive carbonates, metal carbonate, sorry, which is sodium carbonate and potassium carbonate. They are the most reactive metal carbonates, and they too will not break down because they are very unreactive. They're very reactive. So the moment they react with when sodium ion reacts with carbonate or potassium ion reacts with carbonate, right? From being very, very reactive, they become extremely stable. They hold on to the carbonate so strongly due to their high reactivity on their own. So they're very unstable on their own. They hold on to the carbonate so strongly that they become super stable. When they are so stable, even when you heat it up, they do not decompose. They're highly unreactive once they are in carbonate form for sodium metal and potassium metal in their salt form as carbonate, right? They're extremely, extremely stable. So when you heat them up, nothing happens. But for every other metal carbonate, it will decompose, and one of the products will be a gas, which is carbon dioxide. So when the carbon dioxide gas is released, we will be like, okay, this is definitely a carbonate salt. Okay, so and they've told us we can look at it in detail in table 8.2. Okay, so guys, we have table 8.2 here, and I've already done this with you. You see, sodium and potassium carbonate, right? Generally on their own, sodium and potassium are very reactive, but once they have combined with carbonate ion, right, they become extremely stable. So stable that even when you heat it up, they do not decompose, and that's what we are talking about there. Okay, let's move on to the next one, right? So let's talk now about the next group of carbonates. So sodium and potassium, they are one group of carbonates. We've discussed them. Now let's go. We are going from more reactive to least reactive. Right? It's following a reactivity order here, right? So we're going now down the reactivity series. So the next group is from calcium carbonate to copper carbonate. That means following the reactivity series. That means from calcium, magnesium, aluminum, zinc, iron to lead to, and then copper to carbonate. So all these, they have a similar trend. All of them. Okay, all these metal carbonates from calcium to copper carbonate, they will decompose. You heat them up, they will decompose and form a metal oxide, okay, and carbon dioxide. See, that is it, right? So they will just decompose straight and form two products. One of it will be the metal oxide, right, of whatever metal they originally have, and the side product, it's a gas, which is carbon dioxide. So the moment you see carbon dioxide, like, okay, that's the original salt had to be a carbonate salt. Okay, so let's just do an example, right? Okay, so for instance, right, you take calcium carbonate, right? So you heat it up, it will decompose, and it produces what? Metal oxide and carbon dioxide. In this case, the metal is calcium, so it forms calcium oxide and carbon dioxide gas. See, so you know, okay, that's a carbonate. Let's take something in the middle. Zinc carbonate, so automatically should be what? It forms zinc oxide and carbon dioxide. Let's check. Yes, zinc oxide, carbon dioxide. The last one, copper 2 carbonate, right? So copper 2 carbonate, heat it up, will form copper 2 oxide and what? Carbon dioxide. So you see, it is given there, and every other one would follow the same trend. Okay, so this is the second group. The first group was sodium and potassium and sodium to be following the reactivity. Both of those so stable when it's in a carbonate form, does not decompose. Calcium to copper carbonate, when you heat them up, they decompose. They immediately decompose. They form a metal oxide and they will release carbon dioxide gas. So that's that group, right? So take note. Okay, now we move on to the third group, guys. Okay, again, don't forget, we are coming down the reactivity series: mercury, silver, and gold. Gold being the least reactive of the metals. So when it comes to this group, the very low reactivity groups, so mercury, silver, and gold, they are so stable on their own, right? Mercury, silver, and gold. Okay, they are so stable that most of the time you find them on their own. They rarely react with anything else, right? You know, right? Gold is the most stable. Silver, that's why they do not tarnish. They do not, fade, right? They're always lustrous and shiny, right? Why? Because they don't react with the air. They don't react with oxygen to form an oxide. They are normally very, very stable on their own. Hence, they love being on their own. So for these metals, okay, for these metals, when you heat them up, they will want to go back to their original form, okay, because they were stable on their own. So this is the opposite of sodium and potassium. They were very unstable on their own, so they were very reactive. When they became combined with carbonate, they became extremely stable. But for these guys, it's the opposite. Mercury, silver, gold, they are actually very stable on their own. They are very unreactive on their own. But for some reason, maybe with high temperatures or whatever, for some reason, mercury, silver, gold here has reacted with carbonate. But they are, so from stable, by reacting with carbonate, they're actually becoming unstable. They're becoming more reactive. So when you do heat them up, the first thing they want to do is to go back to their most stable form. They want to go back to being metals again. So when you heat up mercury carbonate, silver carbonate, gold carbonate, they will form a metal, then they will form carbon dioxide gas, and because not earlier the metal combined with oxygen, right, now they are on their own, right, they're not combining with oxygen, so that oxygen has to be released separately at the back as oxygen gas, because they're not forming metal oxide, they're forming pure metal like this, right? So they're not combined with the oxide, hence the oxide has to be pushed to the back and released separately as oxygen gas. Okay, so that is basically it. So for these three, which is the second last group we're talking about here, right, they will decompose to form pure metal and become nice and stable and unreactive and happy on their own, right, and release carbon dioxide gas like the others, except now that because they are not forming a metal oxide, the oxygen has to be released separately as oxygen gas, and that's it, right? So it doesn't matter. So let's do an example. Silver, okay, argentum, silver carbonate, right, you heat it up, it's very stable, right, it's a stable metal, so it'll want to go back to its metal form, it'll break down to silver, carbon dioxide and oxygen gas. Same applies to mercury and gold. Alright, and okay, so all that was following the reactivity series. Just ammonium is an outsider, right, you could say, and it's not part of the reactivity series. So this guy is kept separate. Okay, so ammonium carbonate, right? So for ammonium carbonate, basically it will decompose, right? This one you have to memorize. It's just a special scenario on its own. There's no trend to follow or anything like the others. So when you heat up an ammonium carbonate salt, it will immediately break down and form ammonia gas, because it's an ammonium salt, right? Remember we learned any ammonium salt will form ammonia gas, right? So in this case it's ammonium carbonate, it is a carbonate salt, it is also an ammonium salt, so ammonia gas will be released due to the fact that it's an ammonium salt. And then due to the fact that it's a carbonate salt, it is definitely going to release what? Carbon dioxide. Okay, if you take off the ammonia and the carbon dioxide, the only thing you'll have balance from the original reactant will be hydrogen and oxygen. So that hydrogen and oxygen will combine and is released as water, but not as liquid water. And you see it's in gas form, right? So it is as water vapor. Okay, so if you really look closely, you will see that, hey guys, look at that. This is a gas, this is a gas, this is a gas. In other words, everything becomes gas and goes off. Hence you will find nothing left over, no solid particles left over. You heated up a solid and you will be left with nothing, because everything became gas and went off, right? So we say it'll decompose without any residue. That's what they mean, without any residue. That means everything is a gas, right? That's the only time you get no residue. In order to have a residue, it needs to be either solid or liquid or aqueous. Okay, I hope you all understood that. With that, we ended the part on carbonates, right? So basically, these are the trends you need to memorize for carbonates, right? So right down here from ammonium, so you can, okay, we have it all in one frame, okay, right, from potassium to ammonium carbonate, right? So these are the trends you have to memorize, and it's all following the reactivity series, right from potassium to gold, and only ammonium carbonate is a special case on its own. Okay, all right. Okay, if we are done with that, let's move on to nitrate salts. Okay, that means any salt that has a nitrate ion is known as a nitrate salt. So of course, even nitrate salts will decompose when you heat them. Okay, but what is the scenarios for this decomposition? So you look at A for A, sodium nitrate and potassium nitrate produce oxygen gas and nitrites. So please note, nitrate is NO3 minus. Nitrite is NO2 minus. That's it, right? Okay, so nitrate, nitrite. Okay, so if in this case, it said sodium nitrate. Sorry, where was I? Sodium nitrate and potassium nitrate will produce oxygen and nitrites at the back, right? So that is it. So basically, if it was sodium nitrate, it will become sodium nitrite. Okay, and at the same time, it will produce what? Oxygen gas, right? Potassium nitrate will break down to potassium nitrite and produce oxygen gas. That's what they're telling you. So that's one group. That's what we're going to be doing here. But anyway, that's what they're telling you in A. Let's not go too fast. Okay. Okay. And for B, they're telling us other metal nitrates will produce oxygen gas, nitrogen dioxide gas, and metal oxides when heated. So we'll be learning it one by one. So only sodium and potassium have a special scenario, right, where they only produce two products. Everything else produces more than two products. We're going to see. Okay. All right, guys. So I will repeat for sodium and potassium. So they said Sodium and potassium nitrate, okay, when they decompose, they will just break down. You heat it up. So I take here potassium nitrate. I heated it up. It immediately broke down into what? Potassium nitrite, which is NO2. See, so it's potassium nitrite, and it releases. It has lost one oxygen, right? That oxygen is released separately as oxygen gas. Sodium nitrate breaks down to sodium nitrite and releases oxygen gas. So basically, the general formula is sodium and potassium nitrate breaks down to a metal nitrite and releases oxygen gas. Okay, let's move on. Again, guys, we are following the reactivity series. We are going down from most reactive to least reactive, and ammonium will be a special case. Okay, so this is decreasing reactivity. Okay, all right, so let's continue. Now, for the next group, which is again like earlier, like for the carbonate salts, we start at calcium, right? And we end, how did that happen? We start at calcium and sorry guys, we start at calcium and we end at copper, right? So for this whole group from calcium to copper to nitrate, what happens, right? They all will decompose and break down. You heat them up, they break down to a metal oxide, they produce oxygen gas and nitrogen dioxide gas. So there we go, right? So you take calcium nitrate, the first one. We take calcium nitrate, we heat it up, it breaks down to a metal oxide. In this case, it's going to be calcium, so calcium oxide, right? It's also going to immediately, it's going to produce what? Oxygen gas and what? Nitrogen dioxide gas, right? So there we go. Let's do another one, zinc nitrate. Go in the middle, huh? So zinc nitrate, right? You heat it up, it'll break down to what? You already know it's going to break down to metal oxide, oxygen, and nitrogen dioxide. So then it breaks down to metal oxide, which is zinc oxide, oxygen, and nitrogen dioxide. Copper nitrate will break down to copper oxide, right? Oxygen and nitrogen dioxide. So this group, right, that is what they will form. They'll form a metal oxide, oxygen, nitrogen dioxide. As simple as that, guys. Okay? Let's continue, right? Down the order. Then we come to the third group. Same like carbonates. No, not much difference. Huh? It's broken down in the same way, right? Except, of course, right, it's a different salt. So, mercury, silver, and gold nitrate. All of them, okay? Again, remember, mercury, silver, gold, they love being on their own. So, they're not going to break down to metal oxides, right? They're going to break down to pure metal because that's their most stable form. They are extremely, extremely stable and unreactive on their own. So, for instance, so basically, they will all decompose to form a pure metal, their most stable form, and then the same thing, nitrogen dioxide and oxygen gas, right? So an example, let's do silver, right? So silver nitrate, you heat it up, it'll break down to its most stable form, the metal, right? It's going to form pure silver metal, and then of course releases nitrogen dioxide and oxygen gas. Same thing applies for mercury and gold. Okay? And again, ammonium is a special case. So this one you have to memorize it separately. So ammonium nitrate, when you heat it up, okay, what will happen? Well, it will break down, okay, to nitrous oxide. N2O, guys, is nitrous oxide, and it will release water vapor, right? So this is a special case, right, where an ammonium salt doesn't really release ammonia gas. Most of the time ammonium salt releases ammonia gas, but this is a special case. It's not releasing ammonia gas. However, it is releasing nitrous oxide, right, which they use in the Fast and the Furious cars, where they actually, get a boost of thrust, right, by pressing the button, and then nitrous oxide is pumped into the combustion chamber, and combustion is way more aggressive, and so the car engine produces way more power for a short period of time. That's the nitrous oxide we're talking about, if you all are fans of the Fast and the Furious franchise. Then we have water vapor, which also will be produced without any residue again. So again, because both are gas form, so you have no residue at the end. Okay, you get nothing at the end. All right, okay, with that, we have ended even for the nitrate salts. Okay, so you can have a look what we just went through there, right? A few groups, right? Potassium and sodium as one group, calcium to copper, another group, mercury to gold, one group, ammonium, a special group on its own. Okay, all right, guys, let's go to the next one. So we have done ammonium, we've done carbonate, we've done nitrate salts. Now we are moving on to sulfate salts. If you look at number 5, most sulfate salts do not decompose when heated. Only a few sulfates will decompose when heated, and namely they will be iron to sulfate, zinc sulfate, and copper to sulfate. They are the only ones that decompose when heated, and they will produce either sulfur dioxide gas or sulfur trioxide gas, or sulfur dioxide and sulfur trioxide gas along with their metal oxides. Okay, so we're going to see an example, right? Okay, again, all sulfate salts do not decompose except these 3 in your syllabus you need to know, right? So sulfate salts, you heat it up, no, it won't decompose, except if it's iron, zinc, or copper sulfate, right? That's it, right? So let's have a look. If it's iron sulfate, it's a bit unique, right? Because okay, iron 2 sulfate, right? Okay, guys, is going to break down, right? Okay, so you take iron 2 sulfate, is going to break down to iron oxide, sulfur dioxide, and sulfur trioxide. So it's a special case. Why is it a special case? Because okay, it produces both sulfur dioxide and sulfur trioxide together. The others, for instance, zinc sulfate, it will break down and only produce sulfur trioxide gas. Copper sulfate, when you heat it up, it will only produce what? Sulfur trioxide gas, right? Okay, and they all produce a metal oxide along with it, right? But the way we identify it is by looking at the gas, right? So if anything has sulfur dioxide or trioxide gas, then we know it is definitely a sulfate salt. Okay, right? Okay, and when it breaks down, and it can only be one of 3 salts, because all the other sulfates won't decompose. If it does decompose, that means it has to be either iron, zinc, or copper sulfate. So not only we know it's a sulfate salt, we know it's either iron, zinc, or copper. So it's a greater range of narrowing down, right, for sulfate salts we can do by identifying the gas that is produced when you heat it up and decompose it on its own, right? All right, so that is sulfate salts. Okay, I hope you all are clear about that. Let's move on to the last salt, right? This last group of salts, right, which is chloride salts. So number 6 here, all chloride salts are stable on heating except ammonium chloride. Okay, so all chloride salts super stable, okay, except one is not very stable, and that is ammonium chloride. Ammonium chloride sublimes and decomposes to produce ammonia gas and hydrogen chloride gas. Okay, so again, guys, right, just to make it very clear, all chloride salts, you heat them up, they are extremely stable. That means they won't even break down. There's only one chloride salt that will break down. Sulfate salts, all are stable, but there were 3 that break down, right? Chloride salts, very stable, only one will break down, and that is ammonium chloride. Ammonium chloride will sublime. Sublime means from solid it straight becomes gas, right? So it'll sublime and decomposes to produce ammonia gas and hydrogen chloride gas. So again, so ammonium chloride, heat it up, produces ammonia gas, hydrogen chloride gas. Both are gases, so we can say it will decompose and leave no residue, right? So there is no residue. This is a common feature for ammonium salts, to break down into products which are all in gas form, hence not leave a residue behind. Okay, all right, so with that we're done with all the different gases that are released for the different types of salt groups. Okay, so from that we can actually come to a particular deduction. Okay, so that's what they're telling you in number 7. We can, from the salt, from the gases released, we can actually deduce what are the ions present, right? So let's look at table 8.14. If a particular salt decompose and produce carbon dioxide gas, we already know, it's definitely a carbonate ion, right? And then that means it's definitely a carbonate salt, right? It has a carbonate ion inside it. And then if it didn't produce carbon dioxide gas, then definitely we say, hey, that means it's not going to be a carbonate ion. It's not a carbonate salt unless it was what? Sodium and potassium carbonate, because they, even though they are carbonate salts, when you heat them up, they're extremely stable. They will not produce carbon dioxide. So if there's no carbon dioxide produced, it's either not a carbonate salt. If it is a carbonate salt, however, then it's either a sodium or potassium carbonate salt. Okay, do take note. Then next one, okay, let's go for oxygen gas. If ever oxygen gas is produced, okay, right? If it's oxygen gas produced, there's only one ion probability. That means it's a nitrate salt. Okay, the anion is a nitrate. Simple, right? Same thing. If it's nitrogen dioxide and oxygen together, again, like we learned earlier, if it's nitrogen dioxide and oxygen, then again, it's going to be a nitrate ion, except if it's sodium or potassium nitrate. Okay, other than that, definitely it's going to be a nitrate salt. Okay, and then simple sulfur dioxide gas release, then sulfate ion is present. Ammonia gas release, ammonium ion is present. So with that, rather simple. Okay, so it just requires a bit of, yes, I have to admit, you have to do a bit of memorizing, but a lot of it is understanding. If you understand the way the patterns and the trends that are there, then the memorizing becomes much more easier, right? If you want to just memorize word to word, then it takes some time, but if and you're not really gaining knowledge. Whereas if you notice the trend, you notice the patterns, they're going down in the reactivity, and then it's just 3 groups, 4 groups. Ammonia is a special situation. The others are just following logic, because some metals are more reactive, some are less reactive. So the more reactive ones, when they react and become a salt, they are very stable, so they don't decompose easily. The less reactive ones, they are stable on their own, so when they do react and become a salt, they're actually unstable and they will want to decompose and become a pure metal on its own. You see, all those things I told you, because then you understand. There's a lot of understanding that goes with it, and you can use the understanding to memorize, and that makes it easier. Always go for understanding over memorizing if you can. Okay, all right, there are situations, so I have to admit, where you can't do anything but memorize certain things, but in this case, yes, we have to memorize, but please pair that up with a bit of understanding to make yourself understand what's going on better. Okay, all right, so we are done with table 8.14. Let's go back to number 8 on the left here, right? Number 8 on the left. So they said, when a salt is heated, A, the type of gas evolved has to be identified. This will give information on the type of anion or cation present. Okay, so most of the time, if a gas is evolved, it is to identify an anion. The only time a gas is evolved and we identify a cation is if it's an ammonium ion, right? Only when you get ammonia gas, we actually determine the cation, which is ammonium ion. Otherwise, it's always we're determining the anion. For instance, carbon dioxide, it determines that what? It is carbonate. Carbonate is an anion. Oxygen or nitrogen dioxide, it determines that it is what? What is a salt? It is a nitrate salt, right? Okay, so like that, right? Okay, so and nitrate is an anion. If you detect sulfur dioxide, so then it is definitely sulfate ion. It's also an anion. So always the gases tell us what anions are present, except for ammonium ion. When ammonia gas is detected, it tells us the fact that ammonium ion is present, which is a cation. It's the only one that bucks the trend. Okay, it doesn't really follow, right? It's not a follower, right? So that's basically that. Let's go to number 8b. The color change of the solid in the test tube must also be recorded. Okay, this will give information regarding the cation present. So you see, guys, right? Okay, so we had a test tube. Okay, and then we had the solid lah. There's a solid salt, right? So what we did is we heated it up, and then it released a gas. The gas release told us what anion is present, right? Was it right? Was it sulfate? Was it nitrate? Okay, was it carbonate? Right? Was it, what else? Am I missing something? Was it chloride? See, it tells us all the anions present, except in a special case, right? It can actually tell us the cation, and that is for MO. What am I doing? Sorry. Right? Except for ammonium ion. But otherwise, it's always telling us the cation present. So basically, gas release tells us the anion in general. So then how will we find out the cation? If the gas release only tells us the anion, what can we deduce? Is there any way from the same test tube to deduce what is the cation present? Well, after heating, the substance might change color. Okay? If after heating, okay, the substance changes color, right? That means that most of the time it can't tell you what cation is present, okay? But if it is like zinc or lead and these kind of guys, right? Okay, these kind of cations, it actually the change in color will tell you what is the cation present. Okay, so the change in color will indicate what cation is present, but only for very special scenarios, special situations, not for any cation, for special case cations, like I told you, maybe lead, okay, zinc. We'll come to that. We'll come to all those things. Okay, right. So there we are. So basically, gas release will definitely tell you the anion. In a special case, the cation, and the color change most of the time can't tell you anything about the cation, but in special cases, like if it is a certain type of metal, then yes, it can even tell you the cation present, but not most of the time, no lah, right? So we will have a look at all that, okay? In fact, now, right? So let's move on. All right. That was number 8, right? Number 8 done. Okay, right? So, oh, there's a nice diagram, figure 8.8. Why did I draw that? Okay, so they have a nice diagram here. So there you are. Look at this. We heated up the salt. The salt decomposed. When it decomposed, it released the gas, right? The gas will tell you what anion is present, except for ammonium. The ammonia gas will actually tell you it's an ammonium ion, a cation present, special case. And then the residue, right? The change in color, the residue. So what's left behind here is the residue after heating, right? So that residue change of color will tell you what cation is present, but only for certain metals. It can't do it for most of the metals. Certain metals only change color. Most of them will be white at the beginning, white at the end. So you can't really deduce anything. But for some of them, there is changing of color, and then you're like, oh, okay, so in that special case, you can actually deduce the cation by the change in color of the residue. Okay? All right, so let's go to number 9. Okay? They said most salts that decompose produce metal oxides as residue. The change of color during heating gives a good indication towards the type of metal oxide formed as shown in the table. Right, okay, so you see, note, when you heat up a salt, okay, when we heat up a salt, okay, right, so that's a salt, so now we're heating up the salt, right? When you heat up the salt, maybe at the beginning it was a carbonate salt or whatever, right, okay, but after heating, what will be left behind, right? So first it was a, let's say, a metal carbonate, right? But after heating, it will become a metal oxide. This is very common for most of them, right, okay? So they always form oxides, right? So we are going to not observe the color, or we mainly want to observe the color of this metal oxide that is formed, right? So the metal oxide, not the metal, not the original salt. Many students think, oh, it's the color of the original salt. Not really, right? Most of the time, we are looking after heating, a metal oxide is formed, and then we're seeing this color of the metal oxide. This after heating, when it is hot, the metal oxide might be one color, and as it cools down, right, the metal oxide might change color. So it's all about this metal oxide after heating, the product that is formed. Okay, so the color of the metal oxide. Do not get confused. Okay, all right. So let's see the color change of salts on heating, right? So let's say the original color of the salt, the original salt was white. Okay, that means what we started with, not the metal oxide yet. The original color of the salt was white. Then after we heated it up, the residue was yellow when hot. Okay, and white when cold, right? So we know most of the time, guys, this residue, that's our what? Metal oxide. Here again, so here we're talking about the original salt that we started with, and then this is the color of the what? The metal oxide. That's what I was trying to tell you earlier. The final one is the color of the metal oxide produced. So they said this metal oxide was yellow when hot, white when cold. If it was yellow when hot, white when cold, that means it is zinc oxide. Because zinc oxide, when you heat it up, it will be yellow in color. As it cools down, it becomes white in color, right? Okay, so it proves that zinc ions are present in this original salt solution. Okay, so let's say now I heated it up. Okay, let's say we heated up this white color salt. Okay, and in the process, it released carbon dioxide gas. From this, I can deduce the anion. The anion of that original salt, of this original salt right here, is what? Carbonate. Okay, it's a carbonate, right? And then from the residue that was left after heating, it was yellow when hot, white when cold. So I'm like, oh, that means there is it. Okay, so the metal oxide was zinc oxide, and zinc oxide is yellow when hot and white when cold. So if it's zinc oxide, that means the cation is what? Zn2 positive. And so automatically I can deduce, this is zinc carbonate. The original salt we're talking about here was zinc carbonate. See? So gas produce anion, except unless if it's ammonia gas, then it tells you cation, which is ammonium. But yeah, right? So it tells you the anion, and the color of the metal oxide, right, will actually show you the cation present. Okay, so just an example of how we can use this knowledge, right? Let's move on to the next one. Let's say, so we are done with the first one, okay? So let's go to the next one. So this salt, I take this salt and I put it in a test tube. It is white color originally. Now I heat it up. It's not the metal oxide here, it's just a pure salt now. It's white color. I heat it up. After heating it up, right, it forms a metal oxide. Of course, it forms a metal oxide. This metal oxide is brown when it's hot and yellow when it's cold, right? So if ever it's brown, the residue producer, if it's brown when hot, yellow when cold, that means that is lead oxide. If it's lead oxide, that means the cation in lead oxide has to be Pb2 positive. And there you go. You can identify the cation. Then the anion you identify based on what gas is released. Okay, if it's sulfur dioxide, then it is sulfate gas. If it's sulfur dioxide gas, then it's sulfate ion, like that. Okay, right. Then, so that is for this, right? So there we are. We also know how to determine lead ions, right? Next one, if the original salt was blue or green at the beginning, right? And we know blue especially is what? Copper 2 la. But anyway, let's say it was blue or green at the beginning, right? And at the end, after heating up, the residue was black, right? Then you know it's copper oxide. Copper oxide is the only salt in our syllabus that we always use again and again and again that is black in color. If ever after heating something is black in color, I guarantee you 98% chance we're talking about copper 2 oxide. Okay, it's only oxide that is black in color. So automatically if you see, oh okay, after heating it's black, that means yeah, it's copper 2 ions, because what is formed is copper 2 oxide. Alright, and that is that. Okay, so that is done. Let's go to the last one. Let's say it's green or yellow, right? Original one, right? Green or yellow, and then after heating it is pure brown. Well, we have learned before in oxidation and reduction that yes, Fe3 positive is brown in color when it's concentrated. If it's dilute, then it might be yellow in color, right? So there you are. So if the color of the residue is brown in color, then it's Fe3 positive ions. Okay, and there we go. With that, even this is done. All right. Okay, so yeah, most of the time. All right. Okay, so right, okay, any question? Oh yeah, oh guys, sorry, that is for Fe3 positive, right? But if it's green also, okay, if it's green, then it's going to be Fe2 positive, right? If at the beginning it was green, then maybe you're talking about a Fe2 positive ion. If it was yellow in the beginning, then you're talking about a Fe3 positive ion. Sorry, I missed that. Okay, guys, so let's just take that all off, right? Keep the book in its original form. All right, okay, so let's we're done now, right? Okay, so we're actually done with the effect of heat for all the salts. Now we just have to prove it in an activity, but I'm just going to breeze through this activity again because you kind of know it. Huh? So first you might say, okay, we read it in the table, all the things about the carbonate salts. How do we know it's true? How did the scientists get the answers or the conclusions that they came to, right? Are they simply giving us random knowledge? No, not really. As usual, we always have to conduct experiments to get those conclusions, and this is the experiment. The activity 8.7 is the experiment that they would have to have conducted in order to get the results for carbonate salts, right? So let's go and see. It's very simple, right? You put a carbonate salt inside a test tube. We're looking at figure 8.9 now, guys, right? Okay, so you put carbonate salt inside a test tube, right? Then you heat up the carbonate salt, right? And what will it do? It'll release carbon dioxide gas. That carbon dioxide gas will go into the lime water here, and the lime water will become cloudy or chalky, right, or whatever. Okay, they use different terms, right? So it becomes cloudy or chalky, and then you know, yes, carbon dioxide is present, and then now we know if it's carbon dioxide, that means the salt is going to be what? Carbonate ion, right? So we already know the anion here is carbonate, so it's a carbonate salt, right? Okay, so just simple things. Okay, let's move on. Okay, so guys, look at this table here. We can deduce both the cation and anion for some of it, right? Most of the time I told you it really doesn't matter, right? You can't really do it, except I told you when it's what? Maybe special scenarios, like when it's zinc, lead and copper, we can actually deduce the cation present as well. Look at this. From potassium, right, to magnesium, Okay, potassium carbonate to magnesium carbonate, they are originally white color salts. After heating, okay, the residue, which is the metal oxide, the metal oxide was white when it was hot, it was white when it was cold. So this whole information here is useless. It was white. Can it narrow down what is the cation present? No, it cannot, right? So that's why I said most of the time we can't get the cation present by looking at the color of the residue. We have to do other tests to get the cations, okay? But sometimes you can, right? But the point is, in this case, if it is potassium and sodium carbonate, look at that, no visible change in the lime water. So you can't even know whether it's a carbonate salt because it doesn't even release carbon dioxide gas. So for these two first guys, right, you have no clue. You don't know what the cation is, right? And you don't know what the anion is either, right? So nothing you can get from that. However, for calcium and magnesium, right, everything is white. Right, so white, right? So again, right, color tells you cation. So in this case, since everything was white, it really can't tell you anything because most of the time everything is white, right? So most salts are white, so you would not know which salt this is, which cation is here. However, lime water did turn milky or cloudy, right? Okay, or chalky. So when that happens, then you know, okay, definitely we can know the anion because now the anion is carbonate. Okay, it's a carbonate ion. That's the only one that releases carbon dioxide gas to turn lime water milky. See, so then you can get that. Let's go to the next one. Zinc carbonate, right? So yes, there lime water becomes milky. So yes, we know it is the same carbon dioxide is released, so it's carbonate, right? Both the other guys also, lime water becomes milky. So we already know for all three of it at the bottom, it follows magnesium and calcium where the anion is carbonate. They're all definitely carbonate salts. But in this case, because it's zinc, lead and copper, the three guys which you can actually determine the cation by the color of the residues, right? You can actually see for zinc and lead, right? Okay, for zinc started as white after heated. The metal oxide was yellow and hot, white when cold. Definitely this is zinc oxide. So the cation is Zn2. Positive. See, use zinc, and then now we know it's carbonate. So zinc carbonate. Lead. So for lead carbonate, you will see it's white originally. When you heat it up, the oxide produced at the end is brown when it's hot, and as it cools, it becomes yellow. And then that is definitely lead oxide. So in lead oxide, the only cation is Pb2. Positive. Copper carbonate, green originally, becomes black, right? And it hot or cold, the residue stays black. And I told you copper oxide is the only one that's pure black, and so that means it's copper oxide, and the only cation in copper oxide is Cu2. Positive. So we know for these three guys, we actually can get the exact salt just from doing this test, right? Okay, you can know one is zinc carbonate, the next is lead carbonate, and the final one is copper 2 carbonate, right? And that is done. Okay, so I hope from this table itself, you will be able to understand what we are doing, what we just learned, right, for the last half an hour in this video. Okay, all right. Okay, if you have any difficulties, you can WhatsApp me, you could tell us, okay, in the form, you just let me know. I will get back to you personally, right? I will actually go through, okay, whatever you'll say there. You have a problem, I'll even take a picture of the question and I will get back to you, right, on any problems that you're having, okay? But just do give me time. Sometimes it takes 1 or 2 days before I do. It's a very busy time because of COVID. I'm really doing a number of videos and classes and all non-stop. It is really taxing me out right now, but I'm doing it and I will somehow catch up with everything, okay? So please give me time, but yes, I will get back to each and every one of you if you have any questions at all, right? Okay, let's go to activity 8.8. Let me just drink a bit of water. Okay, so just like how in activity 8.7, we determined the effect of heat, right, on carbonate salts. Now we're doing it for nitrate salts. So what are we doing, right? So basically, it's just an activity, guys. So don't get too worried about this, right? Just a general activity. So basically, let's again look at figure 8.10. Please direct your attention there. I will do the explanations for you all, right? So now here we are having you basically have a nitrate salt, okay, and so you're going to heat up the nitrate salt, and then you need to test what gas is released, right? So there's two things, right? We all know when you heat up a nitrate salt, there's two possibilities, right? It could just release oxygen gas, or it could release oxygen gas and nitrogen dioxide gas. So if you're doing nitrate salts, you want to know the anion produced, whether it's nitrate anions. You have to identify whether it's oxygen or nitrogen dioxide. So we have both the tests which we have already talked about earlier. Okay, so in order to test for oxygen gas, you can use a glowing wooden splinter. If oxygen gas is released, like in this case, then it will rekindle this glowing wooden splinter, right? Then, so this is basically in diagram A, we are testing for oxygen gas. Then in diagram B here, you're actually using moist blue litmus paper, right? Okay, because why, guys? Nitrogen dioxide gas is an acidic gas. There's no confirmatory test, but it's an acidic gas, right? So we can prove that. Not really prove it because it's not a confirmatory test, but yes, if you put moist blue litmus paper, it should change to red color due to its acidity. Okay, all right, so that's basically it. So here, basically for diagram B, right, we are testing for the presence of nitrogen dioxide for diagram B. Okay, and we're using a moist blue litmus paper. Okay, so this should turn red. That's what should happen, okay, due to its acidic nature of nitrogen dioxide gas. Okay, so that's it, right? So we're going to do this experiment, and then of course we're also going to look at the color of the residue, right? So all these earlier ones was to determine the anion present. The color of the residue will help us determine the cation present. Okay, so guys, that's that. I'm going to remove this. Okay, let's go to table 8.17, heating test on nitrate salt. So guys, let's start, right? When we're going to break it down to the groups like we had earlier. First, we're going to have sodium and potassium. Okay, then we're going to have magnesium and aluminium. Okay, and then we're going to have the normal zinc, lead and copper, because for them we can determine their cations, because they will actually, the metal oxide at the end will actually have color changes. Okay, so after heating up, so let's start. Okay, so the first group 1, right? Potassium nitrate and sodium nitrate. Okay, can we do anything with the cations? No, you cannot. Why? We don't know anything because everything was white, right? So couldn't do anything, right? The color, so basically cation, nope, couldn't do anything. What about the anion? Let's see. Well, color of gas produced was colorless. Okay, fine. Doesn't tell us much. Hydrogen is colorless. Oxygen is colorless. Many gases are. Nitrogen is colorless. So they're all colorless gases. So it doesn't really tell us much, right? But however, it rekindled a glowing wooden splinter, and that said, hey, right? That means what gas is present? Oxygen gas is present. Okay, and then they put blue litmus paper. It did not change color, so it doesn't tell us anything. So basically we can't get anything from the moist blue litmus paper. Clearly there was no nitrogen dioxide gas given, so it didn't change the color of moist blue litmus paper to red, but it rekindled a glowing splinter. So that means only one gas is released. Oxygen gas was released, and the only nitrates that only release oxygen gas is sodium and potassium nitrate. They only release one gas, that is oxygen gas, without any nitrogen dioxide. So actually you can, because I knew it's originally a nitrate salt, I know like sodium or potassium nitrate, but if I didn't know that, the fact that there's oxygen gas, you can clearly say yes, definitely it's a nitrate salt, right? And then if you know that it's a nitrate salt that is producing oxygen gas, and you do the test of litmus paper and it's not producing nitrogen dioxide, then you know it's very, very clearly either sodium or potassium nitrate. Okay, all right, so that gives us for group 1, right? We can actually know the anion, okay, because of the oxygen gas produced. Okay, and we can deduce that the cation is narrowed down to 2, which is potassium or sodium. For group 2, let's go to group 2 here. Okay, magnesium and aluminium again, right? The cation, nothing can be done, because why? No deduction, because white, yeah, we don't really know what's going to happen there. However, the color of the gas that is produced here is brown. That indicates nitrogen dioxide, because nitrogen dioxide is the only brown gas. Then we can say, okay, to prove nitrogen dioxide, then we put moist blue litmus paper, and guess what? It turns red. So now we know for these guys, okay, there's nitrogen dioxide release. So that already indicates nitrate salt. And then when we tested for oxygen, it rekindled the glowing wooden splinter. So now we know what, there's oxygen and nitrogen dioxide released, right? Okay, so then definitely it's a nitrate salt. Okay, so we can't get the cation, but yes, we know it's a nitrate salt. The anion is clear again, right? Then we go to group 3. Okay, so for group 3 with the same thing lah guys, huh? So the thing is, see, brown and then turns red color. We already know, yes, nitrogen dioxide, and then rekindle glowing wooden splinter, we already know oxygen, and we know oxygen and nitrogen dioxide means what? Definitely all three are nitrate salts. Okay, however, so we know for all of it we can get the cation, the anion, right? Sorry, it's hard to tick at the edge of the screen. Okay, right? So we can definitely get the anion present here. We know the anion is nitrate, but look at that. It was not all just white all the way for the cations, right? Here it was a white solid when hot. White solid originally. When heated, it became a metal oxide that was yellow and hot, white when cold. Ta-da! We know that this is now zinc. Okay, because zinc is the only metal oxide that's yellow and hot and white when cold, right? The other one, white originally, but brown when the metal oxide produced the residue after heating, was brown when hot, yellow when cold, and that indicates that what? It is lead to oxide, right? The last one, okay, was a blue color salt before heating. It became black, didn't matter hot or cold, was just black color. That indicate it is copper ion. So for these three, it's perfect. You can get the anion and we can get the cation for each scenario. Okay, so basically, yeah, so you look at this table and you should be able to come to these deductions almost immediately. Okay guys, so a little bit of memorizing there for the color of zinc, lead, copper, right? Everything else is from the earlier part which we memorized. Nothing new you have to memorize. Okay, so there we go. So that's how they did you can come to the deductions for nitrate salts based on this table, huh? All right, and that is that experiment. Okay, all right guys, now here we're actually starting a new area, huh? Okay, so I just want to quickly cover this, right, and then I will end this video, and the last video will be to test for cations. All right. Okay, I just need maybe 10 more minutes. All right, so now we're doing the next part, which is the test for the presence of anions in aqueous solutions, right? Just for you to know, huh? These are confirmatory tests for many of the anions, right? Okay, so these are finals, but it's only for anions, not for cations. Cations is another long process after this, right? Which I'll do the final video. C will be for video C, right? Okay, will be for the confirmatory test for cations, right? So the anions is only 4 of it, so I just thought I'll just finish it off in this video itself and keep the cations for the last video, right? So okay, let's talk about these confirmatory tests. So basically, let's start here. So tests for the presence of anions in aqueous solutions. Note, right? All these are only when they are in aqueous solutions. This is how we will do the test for aqueous solutions and only concerning the anions. Okay, let's detect the anions in aqueous solutions. So let's start. So they said the presence of anions, which are carbonate ions, nitrate ions, sulfate ions, and chloride ions, can be identified by conducting specific tests on the aqueous salt solution, right? So let's go to the first one. Okay guys, right? So again, right, if you're tired from what we learned earlier, you please pause the video. This is where you pause the video, take a 5 minutes break, and then you come back, right, with a bit more rested mind, and then so you can memorize a little bit more memorizing for each of these ions, right? Okay, so I will now go on to start, okay, with the carbonate ions, right? So okay guys, how will we know if it's a carbonate ion? Okay, so this just said, number one, when dilute acid, okay, it can either be hydrochloric, nitric, sulfuric acid, doesn't matter. Okay, you add it to any aqueous carbonate solution that we want to test, right? Effervescence will occur, right? You can even put it to solid for this one, but anyway, effervescence will occur. That means gas will be given off. The gas that is given off needs to turn, you can run it through lime water, and if it becomes cloudy, that means it's carbon dioxide. And if it's carbon dioxide gas produced, then we know it's carbonate ion. So this is rather easy because we've already learned it, right? If carbon dioxide gas is evolved, it's definitely carbonate ions. Only that in this case, guys, when we are testing directly straight, you want to test for carbonate ions, you don't need to do like earlier, heat up the substance and make it decompose. You could also just heat it, you could just react it directly with an acid, right? Okay, right? So you could just react it with an acid and basically see what gas it gives off. In this case, we reacted it directly with an acid. No heating took place here. It gave off carbon dioxide gas that turned lime water cloudy, and automatically we knew that, haha, right, it's definitely carbonate ions, right? Okay, then we move on to the next one, right? What if we want to test for nitrate ions? This is on the right hand side, okay? So guys, pay close attention. Number one, when dilute, so basically we have a solution here, okay? This is our nitrate solution, right? But let's say we don't know it's a nitrate solution. We want to test if it's a nitrate solution. So the first thing you want to do, you need to add first dilute sulfuric acid. Okay, step one, add dilute sulfuric acid. After that, add in what? Iron 2 sulfate. Okay, that is step 2. You add in iron 2 sulfate. Sorry, I'm resizing the screen. Okay, right. So iron 2 sulfate needs to be added in. Okay, and okay, to your nitrate solution. After that, right, now you have mixed again. What did you add into this? Right, you first added dilute sulfuric acid. Then you added iron 2 sulfate, right? Okay, so this you have already added in. Okay, now the next step is you're going to use a dropper and add drop by drop at the side here. You're going to add what? You're going to add concentrated sulfuric acid. Okay, you're going to add few drops, right, of concentrated sulfuric acid along the side and let it just roll down here. Okay, as it rolls down, if it's really a nitrate salt solution, a brown ring will form in the middle of this solution, right? A brown ring will form, and if that brown ring forms, then guaranteed, yes, this is a nitrate salt. Okay, right? So okay, just again, just to make sure everyone is clear with the brown ring test. Okay, so there we are. We have a salt solution here. Let's call this salt solution X, right? Now, someone asked me, hey, can you please test if salt solution X is a nitrate salt? So I'm saying, okay, fine, right? Okay, so what I'm going to do is, I'm going to now first put in what? I'm going to put dilute sulfuric acid, right? That's step 1. And step 2, right? I'm going to add in iron 2 sulfate, right? And once I'm done with that, the next thing I'm going to do is I'm going to use a dropper. Okay, that's a dropper, guys, right? Again, I'm going to use a dropper and put on the side of the test tube, right? Again, what? Concentrated sulfuric acid, right? And this should go and it should form a brown ring at the middle of the solution. If it does form this brown ring, then I'll say, yes, nitrate ions are present. But if it doesn't form the brown ring, then I would say, okay, this is definitely not a nitrate salt. We have to do other tests and determine what is the anion present. Okay, but if it is a positive test, then definitely you don't need to do anything else. It's guaranteed. It's a confirmatory test. When you say confirmatory, that means definitely only nitrate salt would react this way. Only nitrate ions would react this way, forming this brown ring. Okay, so this is known as the brown ring test for nitrate salts. Please, you need to know. It's very just 3 steps, right? Please memorize the steps. You need to know you have to fix the solutions. It has to be these 2 solutions, sulfuric acid, one concentrated and one dilute, and the other one is iron sulfate, right? That's it, and know how it is done. Okay, all right. Okay, so we're almost done here, guys, for this video. Okay, brown ring test done as well. We can move on. Okay, now what if it is sulfate ions, right? So okay, sulfate ions, number 1. Okay, so if you have a test tube with maybe sulfate salt inside, right? Okay, but you don't know whether it's sulfate salt, right? You want to confirm it's sulfate salt, so you have to do this anion test for sulfate ions. What is the anion test for sulfate ions? This is what you do. Number 1, dilute hydrochloric acid is added to an aqueous sulfate solution that you have in your test tube. Okay, then you need to add barium chloride solution. Okay, if you don't have barium chloride solution, you could use barium nitrate solution. Totally up to you. So again, the point is, what do you add in? You add dilute hydrochloric acid. Okay, after you add dilute hydrochloric acid, you add in either barium chloride or barium nitrate, whichever you have. Okay, and then you will see a white precipitate formed. Okay, again, if it's a sulfate salt, you will find that a white precipitate will form, and that proves that it's a sulfate salt. You know why? Because that white precipitate is actually barium sulfate. Only barium sulfate forms white precipitate. Barium, if it mixes with any other anion, it will not form white precipitate. Only when it mixes with a sulfate anion, it forms white precipitate. So if you see white precipitate, it's guaranteed barium sulfate. If it's barium sulfate, then it's barium sulfate, right? So obviously sulfate ions are there, and that will automatically say that is the positive test for sulfate ion. So all you need to see is, yes, white precipitate forms. You straight know that is what? It's sulfate ions present. Okay? Alright, so basically that is it, okay? For sulfate salt, right? A little bit of memorizing on the which substances to use, so on and so forth. Okay, now guys, there's something you need to know. When doing this test, right, they said you can use dilute hydrochloric acid or dilute nitric acid, okay, but nothing else, either hydrochloric acid or nitric acid. Now, why can't we use, why can't we use sulfuric acid? Okay, students have asked me, why not use sulfuric acid? Because guys, right, let's say even if it's not a sulfate salt, you are putting sulfuric acid. Sulfuric acid already has sulfate ions. So obviously these sulfate ions will go and react with the barium ions, and it will produce a white precipitate of barium sulfate, even if this was not a sulfate salt. So you will get a false positive, because the positive you're getting is for sulfate ions that was not present in the salt solution, but it's coming from this sulfate ions that you put in with your sulfuric acid, your dilute sulfuric acid. So yes, this test you can only do it with hydrochloric acid or nitric acid, okay, but not sulfuric acid. Or what we will say is happening is you're getting a false positive, okay. All right, let's go for chloride ions, right? So here, see, chloride ions, you can use dilute nitric acid. Can you use hydrochloric acid? No guys, because then again, even though there's no chloride ions there, your hydrochloric acid will provide the chloride ions to give the false positive. So you cannot use hydrochloric acid when you're testing for chloride ions, okay? Simple, right? Okay, so let's continue. So here, take dilute, so you have a salt solution, you believe it's chloride ions, you want to prove to yourself or whoever that it's chloride ions. So now you add in dilute nitric acid. That's step one, okay? You add it to the chloride solution. Immediately later, you add what? Silver nitrate, okay? And now what do you get? A white precipitate. Again, just for you to know, if a white precipitate forms, right, it's definitely silver chloride, okay? Because silver chloride, okay, silver only forms a white precipitate when it's mixed with a chloride solution, right? Okay, so it's special scenarios, right? So silver chloride forms a white precipitate, and so if you get a white precipitate, you already know it is silver chloride. And if it's silver chloride, then clearly there is chloride ions, and that's the positive test for chloride salt. So there you go. That's it. Okay, so the question is, why do we add the silver nitrate solution? So that it can provide the silver ions to react with the chloride to form that white precipitate of silver chloride to test to come to a positive test, not a false positive, because we did not use hydrochloric acid, we used nitric acid. Okay, so guys, right, so these are the few things you have to memorize, you have to get this right. These are confirmatory tests for anions, right? And that's the end for anions, right? The next video will be the last part for this chapter, and that is going to be for cation ions, test for cation ions, which is the longest. I mean, it's just few, if you look at it, it's just 2 or 3 pages, or 3 or 4 pages, but it's the most complicated one in terms of so many different things to remember, and that can be a bit tedious. Okay, I totally understand. However, we will push forward and make sure you'll understand this section. Okay guys, so most of it done, just a little bit left. I will do one more video on this and then conclude this chapter as I promised you all, right? Okay, I will see you all in the next video. Please do take care. Yeah, see you all then. All right, thank you.